Hi all, I'm Daniel and this is our new paper on the interplay between label noise and adversarial robustness in the interpolation regime. Everyone listening to this has probably seen this figure way too many times. Our theoretical setting of adversarial risk is that we have mu, a data distribution, and a correct binary classifier f star from R2 to D into 0 and 1, and we take some metric, and the adversarial risk of any classifier f is the probability that if you take x sampled from mu, there exists z for which f of z is different than the true label of x. And in the training set, each label is corrupted, changed to the opposite, with probability eta greater than 0. One of our theorems informally says that any classifier that interpolates this training data, assuming enough label noise, has large adversarial risk when the training set is large enough. So formally we lower bound the adversarial risk of any such interpolating classifier by a constant which is greater than 0, and it depends on the distribution and the label noise. So previously results like this have been proven, but only for very simple distributions such as the union of balls in the given metric, each ball containing only points from one label. Our theorem is much more general, it works for arbitrary distributions. So here we have a distribution and a correct mapping into two colors, orange and green, and we will give the main proof idea, which is to prove that we can find balls of radius rho with large density in one of the colors, and then when we sample our training set, as it's large enough, it hits each chosen ball many times, and when you apply label noise, if the label noise is large enough, each of the chosen balls get hit. And then when you sample x from the distribution, it has a high chance of falling into some of the chosen balls, hence adversarial risk is large. So formally the statement goes as follows: mu and f star as before, the distribution and the classifier. Now we sample a label noise training set from this distribution and classifier, which means that the z's are sampled from mu and the y's are f star of z, except with probability eta is the opposite. The theorem goes as follows: you take some compact subset of the support of the distribution, it has some covering number n, then with high probability you can lower bound the adversarial risk of any classifier which interpolates the training set with a constant times the measure of the compact C, as long as the number of samples m is large enough, and large enough being given by this expression here. So we need some time to digest what's happening here. We have a compact C which we choose. This is an actionable tool theorem. You can plug in some compact C to get the best possible bound, and the best possible bound you get by choosing compact C which has high density but does not have a large covering number, as seen by the number of samples requirement here. This is discussed in the paper. And to remind everyone, a covering number n of a compact C is the minimal number of row balls which covers the compact as in their union. Other stuff we discuss in this paper is that our theorem, which we just described, is kind of tight in the sample size m. So if you take smaller m and we allow arbitrary distributions and classifiers, then there is no guarantee that the adversarial risk is larger than 0. And we also, to connect it with real-world examples of label noise influencing adversarial risk, we prove a theorem saying inductive bias in neural networks and other classifiers can make label noise impact adversarial robustness much stronger. And this is it. Thank you for watching.